Hey, Algebra 1, let's take a look at 8.8. This is exponential growth and decay. We are going to model both the exponential growth and also the exponential decay. These two are very, very similar. The difference between growth and decay is that your growth factor is going to be greater than 1, and then in your decay factor, it's going to be less than 1. So you'll be adding your percentage of growth rate to 1 on the exponential growth, and you will be subtracting your percentage of decay from 1. All right, let's get started. Okay, we have been going over this, so this is the final section with the exponential formula y equals a times b to the x. All right here, this is your base, this is your starting amount, this is your growth factor or decay factor, depending on what the situation calls for. And then x is the number of times it grows or the number of times it decays. All right, so let's take a look at the example for your notes. In 1998, it seems like a very long time ago now that, holy cow. All right, in 1998, a certain town had a population of about 13,000 people. Since 1998, the population has increased about 1.4% a year. Write an equation to model the population increase. Okay, so the general formula, y equals a times b to the x. This is our starting, what we begin with, and this is our growth. Remember, that's going to be 1 plus whatever the percentage is. But we have to convert that percentage into a decimal. And then x would be number of times. All right, so let's take a look at this particular problem one more time. It says in 1998, a certain town had a population of about 13,000. So we're starting at 13,000. Y equals 13,000 times, all right, since 1998, the population has increased, so that's how you know it's a growth, about 1.4% a year. This is a percentage, so to convert that to a decimal, we move it 2 places, and that becomes 0.014. So our growth factor, remember, it's 1 plus whatever this is, so that will be 1.014 to the x power. And that is going to be your equation to model the population increase. All right, for part B, it asks us to use the equation to find the approximate population in 2006. So we need to determine how many years have occurred since 1998. So 2006 minus 1998, and that is going to give us 8 years, right? So putting this in to the model that we came up with in A, we have y equals 13,000 times, I'm going to use parentheses, 1.014 to the 8th power. It just looks better than this. I don't know why. It just seems less cluttered. All right, I'm going to use my calculator, and in this case, it is a graphing calculator because that's what I have up from just doing something with the Algebra 2. All right, we've got 13,000. By the way, if you want this graphing calculator downloaded to your Mac, we can do that. Just let me know. We won't do it during class time, but we can do it after the lesson and after everybody's gone over anything they have questions on. All right, so we've done 13,000 times 1.014. Raise that to the 8th power and press enter. Okay, so we have 14,529.37. Well, with people, we can't have a 0.37 of a person. We either have a person or we don't. We don't care how tall they are. We don't care how young they are. They are either a person or they are not. So let's go ahead and round down to the next whole number since that is less than 0.5. and that gives us 14,529. So we're going to do the approximately 14,529. Is that what I said? Whole, um, yes, okay. Getting old, guys. All right, and that would be the answer to that problem. Yeah, I was going to say, I didn't think there were any other parts. Okay, hopefully that makes sense. Let's go ahead and go on to example 2. This, oh, this will appeal to many of you because this is talking about money, compound interest. You really, really, really want to look at that, and it would be really, really smart of you guys to start investing money now, putting it into savings accounts, but that would even be, I would put it in bonds or something, but definitely in a savings account, and try to do it where you're getting compound interest because you're going to be making money from your money. Your money's just sitting there making money for you, and it's great. All right, so same function, y equals a times b to the x. This is our principal or the starting amount. It means the same thing. Sorry. This would be the growth or the rate, depending on the language. And then this is going to be number of times. Number of times compounded. All right. Suppose you deposit $1,000. That's where I'm starting with. So this will be my A. In a college fund that pays 7.2% interest compounded annually. Okay, so this 7.2% is going to be my rate, right? And I'm going to have to add that, convert that to a decimal and add it to 1. Find the account balance after 5 years. So that's our x. Okay, so setting this up, we have y equals 1,000 times 1. We move the decimal point 2 places, 0.072 to the 5th power. And we're going to use that calculator again. So we've got, let's see if I can do this faster using this. I don't know. 100, no, it's not. Times 1.072 raised to the 5th power. Right, we have 1,415.708. Well, this 8 tells me I need to round this up to the next number, and we're dealing with money, so we do want to go to the hundreds. So this would be 1,415 and 71 cents. 1,415 and 71 cents. So without doing anything except for putting your money in the bank, you have earned $415.71. How groovy is that? It's not a whole lot, but $415 more than you had before. Yep, that's right. All right, let's go ahead and go to example 3. Oh, this table, this is a nice little table that you have here. This one annually, it would be 1 time per year. Semi-annually is twice. Quarterly, 4 times per year. Monthly is 12. So this is what you would do. You would have to take your interest rate and divide it by the number of times it's being compounded in a year. So our favorite is annually because we don't have to do anything to it. You would just divide it by 1, which leaves it as the original number. Okay, so taking a look at example 3, we have suppose the account in the above problem paid interest compounded quarterly, so compounded quarterly, that's 4 times a year, instead of annually, which is just once. Find the account balance after 5 years. Okay, so double checking. We have I have no clue. All right, so we're just going to go with this 1,000 deposit at 7.2% interest. And I guess it's because it was the problem from the earlier screen. That's what it was from example 2. All right, so this is our starting amount. This is our interest rate. And I'm going to convert this to a decimal. So this is 0.072. Now here's what gets interesting. That would be over the course of a year, but we need to know what the interest per quarter would be. So we need to do interest rate per quarter is going to be 0.072 divided by 4. And this will be our B, right? So using the calculator, 0.072, I feel like I should know this off the top of my head. 0.018, okay? So we have that this is 0.018. And we would add this to the 1 for our growth factor. Now, compounded quarterly, so that means every 4 months. Every 3 months, it is being compounded. So we're going to do, it's being done 4 times a year is what I should say. So every year it's being compounded 4 times. Over the course of 5 years, that would be 4 times a year times 5 years. So that is 20 times that it is compounded. Okay, now we have enough information to set this up and solve it. So we have y equals the initial balance, 1,000, times our growth rate, our interest rate, and that's going to be 1 plus 0.018, so 0.018, and raised to the 20th power. Using the handy-dandy calculator, we have 1,000 times 1.018 raised to the 20th. And that is going to give us $1,428.75. So $1428.75. And if you'll notice on that graphing calculator, I still have the previous amount on there, this 1415.71. So we actually earn a whopping $13.04 or 5 cents 4 cents more by compounding it quarterly than by compounding it annually. Not a huge significant difference, but if you have big bucks, it does add up quickly, right? And $13 is $13. All right, last problem. This one, I believe it's the last problem. I could be wrong. We might have example 5 still. All right, decay. Oh, I screwed this one up royally the first time I taught it. It was horrible. I was confused. I was half asleep. I don't know. All right. Technetium-99 has a half-life of 6 hours. Suppose a lab has 80 milligrams of technetium-99. How much technetium-99 is left after 24 hours? Okay, first and foremost, this 99 is part of the name. So don't think this has anything to do with anything. It's just the name, right? Kind of like the Bond movie, Double Agent 07 or whatever it is. Yeah, I know how bad that was. Sorry. Okay, technetium-99 has a half-life of 6 hours. Half-life. That means it's breaking down in half every 6 hours. So its rate of decay is 1/2. And I'm going to put every 6 hours in parentheses Suppose a lab has 80 milligrams, so that's my beginning amount. How much technetium is left after 20 hours? So after 24 hours, that means that we have had 4 half-lives because of 24 divided by 6 gives us 4 half-lives, right? Okay, so let's go over this again before I set it up because I know this can be a little bit overwhelming. So technetium has a half-life. That is our decay rate. So that's where that 1/2 is coming from. And it says every 6 hours. So it's 6 hours. Suppose a lab has 80 milligrams of this particular chemical. So 80 milligrams is what we're beginning with. How much of this chemical is left after 24 hours? Again, if a half-life is 6 hours and we have 24, then it breaks down at 6, at 12, 18, and 24. So that was 4 times. Setting this up as an equation, we have y equals 80 times 1/2 raised to the 4th power. All right, let's go ahead and put that into the calculator to see what we get numerically. 80 times, I'm going to put 0.5 raised to the 4th power. And that gives us 5. That's not much if you think about it, right? So after 24 hours, we have 5 milligrams of technetium-99 left. Hope it's not anything we really need. All right, so final example, modeling exponential decay. This one is a good one. I like this one. Okay, so suppose the population of a certain endangered species has decreased. So that's how you know it's a decay, because it's decreasing, it's going down. They have synonymous terms. They sound alike. They mean very similar things. This rate is at 2.4% each year. So I'm going to write that down. Decay rate is 2.4%. And that is by B, right? Suppose there were 60 of these animals in a given area in 1999. So I'm beginning with 60 animals. And X is obviously going to be the number of years since 1999. So we'll just put number of years since 1999. All right, now to find your decay rate, to put into your function, you are going to subtract this from 1. So let's convert that to a decimal first, and that's 0.024. And we need to subtract this from 1. So we have 1 minus 0.024, which is going to give us 0.976. So this would be our decay factor. This is less than 1. We expect that because it's a decay. If it ended up being greater than 1, we would have had to re-examine what we had put in. All right, now setting this up, we have y equals our beginning amount, 60, times the decay factor, 0.976, and then to the x power. Right? Part B tells us to find the approximate number of animals remaining in 2005. So we need to do 2005 minus 1999, and that is going to leave us with 6 years. So putting 6 in for x, we have y equals 60 times 0.976 to the 6th power. Using the graphing calculator for the calculation, we have 60 times 0.976 raised to the 6th power, and we have 51.86. So this, we're going to go ahead and round that up because it's an approximation. So we have approximately 52 animals. Okay. All right, I hope this has been helpful. Please let me know if there's anything I can do to help you.